So this too should be pretty straightforward. It's more of our triangle geometry. And the only thing different is we may not have a right triangle with this section, but this should be reviewed from, at least part of it, from our geometry days again. We're going to talk about some different shapes, different spaces that we might use triangles for to help find area. So what if our triangles are not right triangles if we want to find the area? Well, generically speaking, the area of a triangle is 1/2 base times height. And if you haven't noticed, in this textbook, they use area variable-wise represented with a K. And so if we had a situation where I've got an area of 1/2 base height, K being equal to my area, what happens here in this triangle ABC where it's not a right triangle? I have to draw. Here's a little review on terminology. What is the line called that comes from a vertex to the opposite side and connects perpendicularly? Altitude. So that's an altitude. And an altitude is the same thing as the height. So it makes a 90-degree connection with the opposite side. And so we can create our own height by dropping these altitudes. Now when you do that, depending on which of the two acute angles you are hanging out at, and which two sides you may or may not have, you can use a trig function to find this value of h. So in this example, we're going to assume that we have a known angle at C, and we have a known value of side A and a known value of side B. And if that were the case, then we should set up a sign of the angle C is equal to opposite over hypotenuse, opposite being h this time. So I know it's kind of confusing. H is usually hypotenuse, but we're talking about the h in this case being the height that we're dropping, the altitude. And the opposite, or the hypotenuse of the little triangle, when I say little triangle, I'm referring to this one. That one right there. The hypotenuse of that would be this side A. And so we find sine of A equals h over A. We find h by multiplying both sides by A, and we get this. Now, geometry proving days. You guys remember triangle congruency? You had a bunch of different acronyms for ways you can prove triangle congruency. One of them was this one, right? Is that one of them? Side angle side. What did that mean? Like a triangle that was set up at the side angle side, how would it have been set up? What would that look like?
Two sides are similar, or two sides are equal, right? And then like an angle.
Okay, it didn't have to be necessarily equal, but specifically, where was the angle if you do two sides? In between them. You guys remember what it was called? Included angle. Yeah, very good. So a side angle side means I've got some side of a triangle, I've got another side of a triangle that create this included angle. And so if you have that set up, you have a situation where you're able to find area of a triangle using one of these three different setups here. Now all of these different ones, B, A, C, A, B, C, B, you'll notice that what happened here is these are all finding angle or areas based off of some given angle. In this first example right here, I know angle C, and that means I've been given a side B and a side A. That stuff would have to be known in order for me to set that part up. In the second one, this one over here, I have angle A, which means I would need C and B as my included sides. And then I can set that on. And then the last one, I know angle B, and then I would have to have been given A and C. So the trick on this, to recognize whether you can use that formula or not, is to look for side angle side setup. Okay? Look for the side angle side setup. Now we're kind of we're getting a little preview of things to come. We're going to talk about two laws coming up in the next couple of days. One of them is called the law of sines, the other one is called the law of cosines. And they kind of deride themselves talk about how the law of sines can help me come up, or use this information to help me come up with the law of sines. But what the laws are for sine and cosine is if I don't have a right triangle, how do I find missing parts of the triangle that's not a right triangle? That's a law of sines. And law of cosine. Things to come. Did everyone, did I go too fast on that? You good on that?
No.
We're good? All right, so what about, let's talk some more vocabulary here. The word regular, when you're referring to a polygon, what does that mean?
It doesn't mean all sides are equal.
All sides are equal and all angles, interior angles, exterior angles are equal. All right, good. And then, oh boy, prefix, hexa. How many sides? 6. All right, let's review our sides. What is a two-sided figure? Is there such thing as a two-sided figure? No. A line can be a two-sided figure. I'm trying to figure. All right, how about a three-sided figure? Four-sided, generically? Quadrilateral. 5? And then 6 is hexa. Now 7 could be both hepta or septa. Hepta or septagon. Octa for 8 was 9. Nonagon, and then 10? Okay. Okay. Check. All right, so anyway, just a little review on our prefix. Oh, here's another word. Boy, we've got all kinds of vocabulary. Inscribed. What does that refer to? Okay, so that means we have a hexagon that is inscribed in a circle, meaning the shape of the circle will cover the hexagon. Now, I remember inscribed, what's the other one called? Inscribed and circumscribed. Circumscribed. Now, there's a difference, obviously. So, inscribed, here's what I do to remember. Inscribed. In an inscribed polygon situation, the vertices, corners of the polygon, another vocabulary term, the vertices are lying on the circle. That's for an inscribed regular polygon. For a circumscribed regular polygon, what happens is, let's see if we can draw one. Oh, that one looks good. Oh, beautiful. See, don't you wish you had one of these? All right, let's see if we can do it. Okay, so that is a circumscribed polygon because it's now on the outside of the circle. The shape is on outside of the circle versus inside the circle. Do you notice where we're hitting the circle in these situations? Where would you describe those little things? Okay, that's true. Tangent, but specifically reference to the sides at the midpoint. You're striking, you're tangentially connecting to the polygon. That's a good word, huh? It is a real word. No, tangential. Yeah. So you're connecting at the midpoints of the sides. So there's the difference between circumscribed versus inscribed. And there, it helps me set up my drawings that when I have to do these little sketches differently. So just be aware of vertices versus midpoints for inscribed versus circumscribed. All right, all that to say, there's our review of our terminology. I think, okay, what is this thing? What does this mean? Unit circle? Yeah, but what is typically unit refer to?
Radius
1. Yeah, this would mean we have a radius of 1. Okay, so here's what we have. We've got this hexagon inside of a circle. And we're supposed to find the area of the hexagon. If this is regular, how many of these triangles will I have that make up this hexagon? 6. All right, see, this isn't rocket science. It's not rocket science. So I have 6 of them. And here's one of them out here. We just pulled it out. And if that is a triangle that results, and I know that has to be an R, that has to be an R. Oh, another vocabulary term. At the middle of the circle is called the what kind of angle? Central angle. Central angle. All right, so we're central angle. What is this central angle? Okay, that's true in terms of radians, but what is it in degrees? 60. 60. How do you know that? There are 6 of them, or 180 divided by 3. Either way you look at it. There are 6 of those angles that make up 360 degrees around the circle. They're all regular, meaning they're the same. So each of those angles has to be 60. Now here's the deal. What kind of triangle is this little triangle? If that angle is 60. Okay, now just because it's 60 doesn't make it equilateral. It's 60 because these two sides make this triangle. Before you know it's equilateral, you know it is what? Isosceles. And so if it's isosceles, that means those two angles need to be the same. And that means I have 120 degrees to balance between two angles, which means, guess what? Those two angles have to be 60. That is what makes this an equilateral triangle. All right? Makes sense? Okay. So now, how do we find the area of that thing? Remember our new cool formula. I do not need to know a height to be able to use the formula. All I need to know 3 things. I need to know a side, an included angle, and another side. Do I have that in this situation? I do. So I have, if we call, there's my side, there's my included angle, there's my other side. I'm able to find the area of that triangle just through K equal 1/2. For generic purposes, I'm just going to use A, B, and C. And don't get hung up on the letters. Just hung up on what they mean is probably more important. Don't get hung up on it, but know what they mean. So the A and B are the sides that surround the angle that I know. And I know R and R, or in this case it's a unit circle, so we can say 1. So I have 1/2 of 1 times the sine of 60 degrees. We can do all of this without a calculator. 1/2 times √3 over 2, which is what the sine of 60 is. Meaning the area of one of those little triangles is √3 over 4. But is that my answer? Is that the area of the hexagon? No, now I got to multiply by 6. So now that I know that there are 6 of those equal little triangles in there, I can find the total area of the hexagon. It's equal to 6 times what we just found is the area of one of those. And we get 3 √3 over 2. Now, were there units involved? So what do we write if there are no units? We write units squared. Don't forget to include the units. That is the area, the exact area, by the way, no decimals, but that's the exact area of that hexagon, given a unit circle with radius 20. So that's really that's all geometry stuff. Yeah, it's not that bad. What questions arise from this problem? Anything? Yes, sir.
How do you know it's side equal side again?
So a side angle side means I have 2 adjacent sides and an included angle. So if I have a radius of a circle, I have to know that the other side, which is also a radius, those are the same thing, given, because it's a unit circle. And we're at the center of the circle with a central angle that has 6 equal parts, meaning 360 divided by 6 makes that 60 degrees. So there's my side, my angle, my section. They have to go in that order. Yeah. Okay, very good. Let's move on to some other stuff. This is a tag teamer. I just want you guys to pair up, see if you can do this. Given this information, can we find, notice it says all the possible values, meaning there can be probably, it says all, more than one angle of C. So I'll give you guys a couple minute or two, see if you can pair up, come up with some answers here, and then we'll see how we did. So, a couple different approaches. I'd like you to, again, this helps you get to know your formulas. I am generically using A, B's, and C's. It just so happens that that's what we were looking for and what we have. So, filling this in, I have a K, which is 12 centimeters squared, an A, which is a 3, a B, which is an 11, and a sine C. Now, I want to sure, before I start filling numbers in, I want to make sure that the two given sides and the angle we're looking for are side angle side setup. So 11, 3, angle we are looking for, it is side angle side setup, so we can use this formula. So we go ahead and move everything around. We get, what, 24 divided by 33, which is going to be 8/11ths, is equal to the sine of C. How did I do that? Oh. Multiplied by 2 divided by 33, and then reduced, if you're wondering. So we want to find C, which is the inverse sine of 8/11ths. And this is where you guys found, what is it, 46.6 degrees. Now, here's the deal. You're trying to find a situation. We cannot forget what we just finished doing. You have two places where sine is positive, here and here. So we're looking for those two angles. And by doing inverse sine the first time, we'll call that one theta 1 because it's quadrant number 1. That's your referencing because it's less than 90. So I'd apply that reference angle over here, and then 180 minus that would be 133.4. Those would be my two answers. That could produce an area that has a 12 centimeter squared area and those given sides. Yes?
How would that work in that triangle?
How would that work in that triangle? That's a good question.
Plug in that.
Okay, let's draw a little sketch of what's going on. So we have two sides that are locked. Their length cannot change. A to B. The angle we can see is fluctuating for C. So this is actually a precursor to a special case for the law of sines called an ambiguous case. So let's draw the first one. Let's draw it with a 46.6. We have an 11 and we have a 3. I know it's not quite proportional, is it? Maybe that a little better. So then I would produce this side over here with a 46.6 degree angle. Correct? Well, let's open that angle up. We still have an 11. We still have a 3. But now it's just obtuse.
So you're letting it change the hypotenuse.
Yeah, the only thing that's changing is, well, a couple of things. This angle, that angle, and whatever my hypotenuse value is going to change. But it's the same area. Get it? So that's how come we get two answers. Okay? So you would have kept going on yours. Once you found your H, then you could set up and try it. So Joey, what he did is he just said, if I know area, generically 1/2 base height, my base is 11, he went and found H. And once you know H, you can go ahead and find your angles. That's another way. Any questions on that? Pretty low complexity so far? Yeah, pretty simple. Yeah, the laws that we get to, they make it a little more interesting. All right, how about this? More terminology. There's a lot of vocabulary thrown at you today. Segment versus. So what do we use to say that? Not section. Sector. Right? Segment versus a sector. So we just got done with lunch. And of course, when we talk about circles, we talk about which of our favorite food items? Pizza. We talk about pizza. And so let's define our new terminology based off of pizza descriptions. So let's talk about sector first of all. Out comes the nice barbecue chicken pizza from California Pizza Kitchen with your honey wheat dough. And the sector would be what? How would you describe the sector for our pizza? What is that? What are we referring to? It's a slice. A slice of the pizza is your sector. So, I only have them slice my pizza into 3 parts. So there's my first slice of pizza. I eat it in 3 slices. Maybe 5. Sometimes I roll the pizza up and eat it like a burrito. So there is a sector. The sector is like the slice, the entire slice. Then there are those odd people on the planet of the Earth who do weird things with their pizza, such as they do this. Okay, we have 2 points on the outside of my circle somewhere. And I connect these 2 points with this line. And that line is called a chord. And I get this shaded yellow area. So this is like the person who takes their slice of pizza and then cuts off the inside part of the slice and just eats the crust. Who does that? You just eat the crust? Why don't you just order bread? Who eats the inside of the pizza? Oh, man. You're crazy.
I don't just eat the crust, like a little bit of.
Yeah, you have a little bit. Yeah, you see, like you have a little bit of the slice right there. Just a little bit. Yeah, maybe. All right. So the person who does that, Chloe, is the person who eats just the segment of the circle. It's the sector, the sliced pizza, removing the triangular good part of the pizza. And then you just get the crust part of the pizza. That's the segment. All right? So there's our definition in pizza speak for how we can describe a segment. It's just this shaded area. It's a part of the sector, but it's the bad part. It's not the good inside parts of the sliced pizza. It's just the carbohydrate parts. Yeah. Okay. So there's our new terminology, segment, sector. We already do that. Segment is this bounded region by a chord and the arc length attaching those 2 points for that chord. So it's a pretty simple formula if we think of it as like removing out of the sector the triangle that we see in here. So here's our right, not necessarily right, but here's our triangle inside of our sector, and we're removing that. There it is. I'm subtracting the area of that triangle from the area of this sector in blue, and we get the area of the segment. All right. What about these segments? How big can they be? Let's see. Watch this. Oh, look at that. Isn't that fun? So you can drag. Here's the area of our shaded region is, again, defining our segment. Now, unlike a sector, we said a sector can go anywhere from 1 degree all the way to 360. You can have a full circle. Is that true for a segment? Let's see what happens. So I get down here where I am now the, what part of the circle? What part of the circle am I right? Oh, look what happens. I get to the diameter, I go one little click past it, so 180 plus 0.01 or something, and I'm back to a situation where I just have half a circle. So a segment is never bigger than half a circle. Can't be a full circle. Area-wise. How small can it be? Well, it can kind of pretty much be almost nothing. There's still a little sliver right there where points A and B are. There's a little chord that connects them, and there's still a little arc length, but it's just hard to see it. So the closer these points obviously get to one another, smaller our chord, smaller our sector, smaller our segment. And there we have it. Wonderful. Got a little Marvin Gaye going on. Good stuff. That's good stuff, right? All right, so let's do this thing. Being careful with units, I'm going to be emphasizing units for these problems. Area, we're talking about feet squared, inches squared, centimeters squared, whatever. So here we have circle. Usually, if you haven't noticed already, probably in geometry, you guys already did this. You name a circle typically by a variable, right? And it's named off of the center of the circle. So circle P, center circle P. Has a radius of 3 feet, central angle of 85 degrees. Now these could be in radians as well. So either way, you can still work them out. We're going to have to go back and remember formulas from previous chapters that dealt with sectors. So remember we had K equal, all right, who's got it? Who remembers? The area of a sector Good job. And then what was it when it was degrees?
1.5 figured 365
Say it over 360 times pi r squared. Yep. So those are our areas of sectors, depending on if I was in radians or degrees. So here's what I would do. You know, we draw a little, there I am, point P, 85 degrees. Yeah, that's about 85 degrees. That was 85 degrees. And then we can create our pizza slice. All right, let's complete the circle. But that's not a very good circle. That one got pushed up against the back wall of the brick oven.
Oh, I did it.
Yeah.
See, that's burnt.
Okay, it burns fine. That's okay. That burns. All right, so there's our their whole circle, and we want to find the area of the segment. So again, segments are created by connecting the endpoints of my arc, and the area that results is the segments. We're trying to find that. That's my segments. Right. All right. Now that we have that all squared away, we can label all the things that we know: 3 feet, 3 feet, central angle of 85, and then now we can find our answer. So we should start with our generic formula again. So let's see, area of segment equals area of sector minus the triangular part inside of that segment. And now we just fill in our equations here. So we're in degrees, so we got to use the correct sector area formula. So that was going to be which one? Which one do we use for degrees? Yeah, the theta over 360. So we have theta 360 times pi r squared. And we're going to remove from that. What? What am I going to remove? Generic formula. 1/2. Yeah. 1/2. Some side, some other side, and it's included in. So that's generically what we've got for the area of our segment. All right, you guys plug them in and tell me what you get. What happens when all this stuff gets plugged in? What's that little blue sliver? So plugging it in, and we are in feet, so we got to make sure we include the units. Area of segment 2.19 squared. All right. Not too shabby, right? We good on this? Any questions that we need to do before we